in the last lecture I had told you that if the linear programming problem, as we have been defining the standard version, I have been referring to it as LPP3, if it has a optimal solution, then it will have, then a basic feasible solution will also be an optimal solution. And then I also showed you that if B is a basis for the same linear programming problem, then I can always find a vector cost vector C such that B is the optimal solution for that corresponding to that cost function. So, after that we now start developing the simplex algorithm, and let me now start building up and computing the quantities that we need to proceed with the simplex algorithm. So, the first thing is, you see, so we always have this LPP, which I am calling as 3, is minimize C transpose x subject to Ax equal to B, x greater than or equal to 0. So, for this LPP, suppose B is a basis that gives a feasible solution, that gives a basic feasible solution x b 0. And here again I am using this notation that I have renumbered the variables and the corresponding columns of A, so that the first m variables are your basic variables and the others are non basic variables, and they are 0, right. So, now I need to first have the quantities, yes. So, need yj as B inverse Aj, right, because then only I can pivot on an element here corresponding to. So, I had already developed these formulae for you earlier anyway. So, now this is B inverse Aj. So, I need to compute this. Once I have this, then I can compute my yj. So, I will try to show you an iterative method for computing B inverse, which requires, which makes up the, which uses up the calculations made earlier for 1B, and then when we change the basis, how do we update our basis inverse. So, this is the whole idea. So, let me show you. So, the idea here is that to compute B inverse, we use elementary row operations. So, everybody is familiar with elementary row operations. We use it on the matrix, on the enlarged matrix, B I, where I is of the same size as B, that is, it is m cross m. Okay. So, I do this and I reduce this to I, then what you get here is your P inverse, because by elementary row operations I start making the first column as 1 0 0, second column as 0 1 0 0, and so on. When I do this, what happens is that you get this on the right hand side. So, this is how you compute the B inverse, right. Okay. Now, suppose Aj replaces column Br of D, right. And I told you the rule for this, so that you get a basic feasible solution. We will revisit it again, but anyway. So, suppose it replaces this, right. So, I need, so, and let B prime equal to B1 Br minus 1 Aj Br plus 1 Bm. This is the new basis. Yes, let this denote the new basis. Okay. So, now I would need to compute the inverse of B prime also, and if I have to do it from ab initio, it will take lot of time, and so I want to show you. So, the thing is that if suppose I carried my column Aj along with when I was doing these elementary row operations, in other words, if you multiply, consider B inverse of B1 BR minus 1 AJ BR plus 1 BM. Now, since B inverse is the inverse of B1 B2 BR BM, you see this will reduce, this is actually E1 to ER minus 1, right. These are unit vectors with, this is 1 in the first place, this has 1 in the R minus 1th place, and this will B inverse AJ is your Yj by our definition, right. This is Yj, and these are again all ER plus 1 EM. So, in other words, I already have this, and if I have Yj with me, then in order to compute the B prime inverse, I simply have to reduce Yj to the corresponding ER by elementary row operations, right. Is it okay? So, in other words, what I am saying is that you start with, you want to compute the inverse of B prime. So, we would have to reduce this to identity matrix. If you have already multiplied it by B, then what you have here is E1 ER minus 1 Yj ER plus 1 EM, and here you have your B inverse, right, because I have pre-multiplied, sorry, this is B inverse. So, I have pre-multiplied the whole thing, right. Now, in order to reduce this, so once I reduce this to ER, then, and I do all the elementary row operations for the whole row together, then what I will have here would be my B prime inverse, and this is the whole idea. So, in other words, I do not have to reduce my B prime from the beginning to an identity matrix. I already have done that much work. So, these m minus 1 columns are already reduced to identity form. I need to do this, right. And Yrj, so Yrj is the pivot element, Remember, we said that Yrj has to be positive and the ratio has to be minimum for the new solution, for the new basis to correspond to a feasible solution. So, we have discussed all that. So, Yrj is the pivot element. So, when I reduce this finally to identity here, what I have will be B prime inverse. Okay. So, this is the crucial point here. All I am saying is that iteratively I am able to compute my new basis inverse at each iteration. So, once I have computed this, then I can just do pivoting on one column, the column that I have brought into the basis, and if I already have these quantities with me, then I do not need to multiply B inverse AJ. Remember, each operation costs something in the computer, and the idea is that you try to make your computations as minimal as possible and as fast as possible. That is the idea. So, here I am able to use my earlier computations for B inverse, for computing B inverse, and then by simply doing m more operations is a pivot, and so on. So, therefore, B prime inverse could be computed by using m elementary row operations only. Okay. So, instead of doing it for the whole this thing, and of course, we do it for the corresponding columns of B prime here, whatever B inverse here also, to get this thing, right. Okay. So, then I have shown you how to go from one basis inverse to another, right. But then we need a few more computations. So, anyway, let me then take up an example here and show you the how we suppose you have this system of equations. Consider the system of equations x1 plus 2x2 plus x3 is equal to 6 minus 2x1 plus x2 plus x4 is equal to 4, 5x1 plus 3x2 plus x5 is equal to 16, and your variables x1, x2, x3, x4, x5 are all non-negative. Okay. So, let me start with B, with my basis B as consisting of 1 minus 2 5 0 1 0 0 0 1. Right. That means my basis B consists of 1 minus 2 5, which is A1, A1, A4, A5. These are the columns. I am not renumbering them here because now I will be actually computing it for you. So, therefore, you can see what is happening. Fine. So, we said that we will use elementary row operations of 1 minus 2 5 0 1 0 0 0 1 and 1 0 0 0 1 0. Right. Okay. So, you want to simply reduce this to identity to E1, which means that twice this you add here and 5 times the first row you subtract. So, I will do both the operations in one go, and that will give you 1 0 0. So, the top row does not change here, 0 0. Then twice this you are adding here. So, that makes it a 0 here, this is 0, and twice this you are adding. So, 2 1 0, right. Then 5 times we are subtracting the first row from the last row, which makes this 0 0 1, right, and 5 times. So, this is minus 5 0 1. So, you can verify that this is now P inverse. Okay. So, elementary row operations helped us to obtain the inverse of this matrix, given matrix B. Right. Now, suppose I induct column A2 into the basis. Right. And so, I will need, so the idea is that if I already have this quantity with me, the scalars that I need, see, it is clear that what I would need y2 is B inverse A2. That means, these are the scalars that I need for expressing the column A2 as a linear combination of the basic columns, right. So, what is my y2? Y2 would be B inverse. So, B inverse now is 1 0 0 2 1 0 minus 5 0 1 times the second column, which is 2 1 3. So, that is 2 1 3, and so that gives me 2, and this is 4 plus 1 5, and then it is minus 10 plus 3, which is minus 7. Right. So, I need to now compute. So, now my B prime, the new basis inverse. So, B prime right now is, oh okay, I do not know, yeah, fine, sorry. So, all the components here are non-zero. So, I could replace A2 by any of the basic columns, but since I want a basic feasible solution, this one is out. I can either replace B1 by A2 or B2 by A2. So, let us choose this one. Okay. Suppose I choose this one. That means, now my B prime will be, B prime is will be your A1, A2 and A5, right. The second column here, which was earlier A4, I am replacing it by A2. Okay. And now I need B prime inverse. So, to compute B prime inverse, that is what I was saying, that here you have already, see, in this thing I start with, so if you consider the matrix, A1 is 1 minus 2 5. Now, A2 is 2, 1 and 3, 2, 1 and 3, and this is 0, 0, 1. So, I need to compute. The idea is 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah, I will do this, but if I multiply this by B inverse, then what do I have? This will reduce to identity matrix already. So, identity vector. So, this will be 1, 0, 0, and B inverse A2 I already know is 2, 5 and minus 7. So, 2, 5 and minus 7, and this is 0, 0, 1. And so, on this side it will be B inverse, which is 1, 0, 0, 2, 1, 0, minus 5, 0, 1. Oh no, sorry. So, here B inverse, this is B inverse, right. So, because I have multiplied the whole tableau by, so this is equal to this. So, here you have, now this is the thing, you need to reduce this to the identity vector, which is E2 here. So, the second basis vector. So, I will reduce it to E2 and do some elementary operations, and in the process what I get here would be then my new basis inverse. So, since I have to pivot on this one, so let us do the calculations here. I divide the whole thing by 5. So, that makes this 5 and this makes this 1 by 5, and this becomes 1. Okay. Now, twice you subtract from here. So, then this becomes 0. Twice I subtract from here. So, 1 minus 4 by 5 will be 1 by 5, and this will be minus 2 by 5, and this is 0, right. Then 7 times this row I have to add here. So, 7 times you do it, this will become 0, and 7 times I am adding here. So, this is minus 5 plus 14 by 5, which is minus 25 plus 14. So, that will be minus 11 by 5, minus 11 by 5. 7 times this you are adding, so that becomes 7 by 5, and that is it. So, I have my new basis inverse. Okay. So, this is the whole idea. So, just for one column I had to reduce one column, and then I could get, and using my computations for B inverse, I could now compute my B prime inverse, because B prime inverse differs from B prime differs from B in exactly one column. So, why do the calculations from the beginning, and we can make use of this, right. Okay. Now comes the next step. So, that means I have sort of given you a way, not a very organized thing right now. I will give you the simplex tableau and then give you the organized way of, but anyway we know how to go from one basic feasible solution to another. Yeah. In fact, right now I have given you the formula to compute the basis inverse from one basis inverse to another basis inverse, how to do that. But then we need a few more things, and this is we want to go to a basic feasible solution which improves the value of the objective function. See, the idea for the when we progress with a simplex algorithm is to be able to move from one basic feasible solution to another, and in the process I also improve the value of the objective function, and in our case the objective function is a minimization function. So, therefore, I need to reduce the value of the objective function. So, how do we do that, right. So, now let me just recall the transformation formulae. So, I will recall the transformation formulae, right. And what did we say, that when AJ replaced column BR, right, the notation is all clear, then our new XBI prime was given by XBI minus YRJ into X. This will be the transformation formulae. This is your XBI minus YIJ. Okay, this is YIJ upon YRJ. This is would be, yeah, XBR when I is not equal to when I is not equal to r, because for I equal to r, of course, this becomes 0. Remember, xbr has been made 0. The new, in the new basis, the rth, the old basic variable has been made 0, been non basic, and you have your xj prime equal to theta, which is your xbr upon yrj, and this is greater than 0 because yrj is positive. Remember, that is why we pivot on yrj. So, yrj is something which is strictly positive, and then this is your new basic field. So, this is your transformation formulae, right. Okay. And using this transformation formulae, let us see what would be. So, I will keep that intact. So, what I am now going to say is to how to move from one basic feasible solution to another and improve the value of the objective function. Okay, because this is our ultimate aim. We want to go on improving the value till we can no further improve on it, and that gives us the. Okay. So, let us see the value. So, your z prime corresponding to b prime is what? Since that is your basic feasible solution, new basic, this is CBI into XBI minus XBR upon YRJ into YIJ, this summation I varying from 1 to m. See, I will include I equal to r in the summation, because as we have seen, for I equal to r, this number becomes 0, right. So, therefore, the contribution to this sum will be 0. So, therefore, I will just keep it like this, because that will help us to plus your XBR upon YRJ into Cj, because the jth variable has now become basic variable, right. This we also refer to as theta, right. So, now you see, when you sum CBI XBI is your old objective function value summation I will, that is why I kept the summation from 1 to m, not excluding I equal to r, and then you have plus, see here, if you write Cj XBR upon YRJ, we are writing as theta, then this is CBI. So, minus summation CBI Yij, I varying from 1 to m, this times theta, right. Now, we give this quantity a special name, because okay, this is Zj, let me call it Zj, corresponding to the column Aj, right. So, this is equal to Zb plus Cj minus Zj into theta. Theta is positive. So, now you see, if you want the value z prime b prime to be less than Zb, then obviously you want this to be less than 0, okay, less than or equal to 0. If Cj minus Zj is positive, then by including Aj into the basis, your value of the objective function is going to go up. So, this is what we, so therefore, I need to compute these quantities also, and so you see that for this I need my Yij's and your value theta. So, when we write down the simplex tableau, I will show you how we compute all these quantities at this one at the same time. Okay. So, Cj minus Zj, if it is less than 0, then the value will definitely improve. Equal to 0, the value will remain the same, right. So, therefore, and we call Cj minus Zj as the relative prices, relative cost of Xj. So, relative cost, because this is the rate of increase. You can, there are many interpretations to Cj minus Zj that one can give, and this, as you see, that for 1 unit increase in the value of Xj, that if theta is 1, then the value of the objective function changes by Cj minus Zj. And remember, because we have assumed linearity axioms, proportionality and so on, when there is an increase of theta in the value of x j, the total increase in the value of the objective function is C j minus Z j into theta, right. So, this will be your this thing, and now we can right. So, therefore, you now that means we know that we can go from one basic feasible solution to another, and in the process improve the value of the objective function. That means now yeah, let me just begin with this. So, you have n minus m non basic variables, right. So, that means any of these n minus m columns can come into the basis depending on the condition being satisfied. That means, when they come into the basis, the new objective function, the new basic feasible, new solution should also be basic feasible, and so on. So, we have choices, so we can do this, but then that means I should have computed C j minus Z j for all these non basic columns n minus m, and then I choose the ones for which there is an improvement in the value of the objective function. And as Danzig in his initial simplex algorithm specified that let us go for that column for which C j minus Z j is most negative, because then you improve, supposedly you improve the value of the objective function by a large amount, but that is not correct, because the value of the objective function changes by C j minus Z j into theta. So, a non basic column for which variable for which C j minus Z j is very small, that means in magnitude it is large, it is a negative number, but the corresponding theta may be small. So, that part is there, but in any case for all practical purposes this was being used as a rule to enter a non basic variable into the basis, and then I will later on discuss the other ramifications of this rule, because it was shown to be a little unpractical. And so, therefore, so now that means in a nutshell the algorithm is that you start with a basic feasible solution, you compute the C j minus Z j's. If all C j minus Z j's are greater than or equal to 0, you cannot improve the value of the objective function, and I have already given you this optimality criteria, we discussed it some time ago. So, therefore, if at a basic feasible solution you have C j minus Z j's are all non negative, you will say that the current solution is optimal. Okay. And if you have some C j minus Z j's which are less than 0, then I will bring that column into the basis and then compute the new C j minus Z j's, check for optimality criteria, and proceed till I hit the optimality criteria. Okay. So, two things are possible at this point. When we go from B to, so I move from B to B prime. Now, two things are possible. Two things are possible. One is, or in other words, actually from B to B prime I proceed, two things are possible. All C j minus Z j, which we also refer to as C j bars, it's convenient. Okay. So, these are greater than or equal to 0. This would imply, this implies that the current solution is optimal, okay, because we have the optimality criteria. Or what will the second thing, that C j minus Z j is less than 0 for some j, and the corresponding vector is all less than or equal to 0. Remember, to move from one basic feasible solution to another, I needed the condition that my YRJ, the element on which I want to pivot, should be positive. Now, if I want to see C j minus Z j is less than 0, so I want to bring this into the corresponding column A j into the basis, but I cannot proceed with a simplex algorithm, because all entries under the column A j are less than or equal to 0, and I need at least one pivot element which is positive. So, we will we cannot proceed with the simplex algorithm here, but then we can make certain conclusions about the problem. So, let us see how do we see. I want to show you that if Cj minus Zj is less than 0 and for some j and Yj is all components of Yj are less than or equal to 0, then you can show that the problem is actually unbounded. So, if this happens for some j and this, then the problem is unbounded. And if you remember our discussion earlier, I showed you that unboundedness means that your polyhedron has a direction, and now actually we will say that we will show you that it is a direction along which the value of the objective function is decreasing. So, if there is a direction in the polyhedron and along that direction you by moving along that direction you can improve keep on improving the value of the objective function. That means it can be made as small as you wish. This is the whole idea, right. Okay, so let us see. Now, remember your Yj is nothing but B inverse Aj, or in other words this implies that you can write Aj as summation Yij Bi, I varying from 1 to m, or I can write this as minus summation Yij Bi, I varying from 1 to m plus Aj is equal to 0. And since all Yj's are, the vector Yj has all components less than or equal to 0, it means that Yij's are all negative or 0. So, minus this is all positive. So, therefore, you have here, this implies that minus Yj, then 0 0 1 0 0, this is minus, this is a feasible solution, right. All components of this solution are non-negative and no, it is not a feasible, I am sorry, this is not a feasible solution. So, this implies that this is non-negative. As a vector, it is non-negative, right, it is a non-negative vector, and from here it follows, and your A of, let me call this as, okay, let me call the, because we have been giving it a name. So, this is, let me call this, and A D is 0. So, D is a non-negative vector and such that A of D is 0, right. So, this implies that when you write x b 0 plus theta d, right, this is a, if we consider this, then A of x b 0 plus theta d is actually B, because A of D is 0 and this is already a basic feasible solution. So, this is equal to B, right, and it is the components here as I have shown you are all non-negative, because components of x b are non-negative, components of d are non-negative, and this is true for all theta greater than 0, actually greater than or equal to 0, but so therefore, you see that the solution remains feasible no matter what the value of theta. I can take the value of theta as big as I wish and I will remain in the feasible region. So, this is the direction, this is a direction which is present in your feasible set, that is the direction of the polygon, right. So, this is what you have, right. So, therefore, when you have Yj's are all non-negative or all negative or 0, then I can show you the existence of a direction in the feasible set, right. And now compute the value of the objective function. So, from here you see, if you do this, let me, or okay, I will compute. So, therefore, the value of the objective function for the feasible solution. Remember, it is not a basic feasible solution, because it has m plus 1 components, right. This feasible solution has this vector D has m plus 1 components, non-negative, right, and this has m component. So, the sum has m plus 1. So, this is only a feasible solution. And if you remember, if you recall your this thing, I showed you that you have this, then there is a direction present, then you can go move along this direction and remain feasible, right. So, therefore, when you move along this direction, you are no longer at a basic feasible solution, because you are not, you are in the interior of the feasible region. Okay. So, that part has to be taken. Therefore, the value of the objective function for the feasible solution x b 0 plus theta d is, see, remember CBI. So, this will be this will be summation CBI XBI. Yeah, just be a little patient and we will be able to write down. From here you will get plus theta minus Yij, right. So, this whole thing summation I varying from 1 to m, the same expression actually, plus theta Cj. So, exactly what you get from here. The only thing is, yeah, so therefore, this becomes Zb plus theta times Cj minus Zj, the same expression, right. The only thing is that now here Cj minus Zj is less than 0 and theta can take any positive value. So, you see that this can be made to go to minus infinity. I can go on increasing theta, and that is the idea, that I am moving along this direction. My value of the objective function is decreasing as I move along this direction, and so I can make the value of the objective function as small as I wish. Okay. So, this shows that the problem is unbounded. So, the moment you encounter this situation, you can stop, because your problem is unbounded. So, we will not be able to obtain a finite optimal solution, right. Okay. So, now let us demonstrate this. I will show you the steps of the simplex algorithm through an example. Maybe we will take this example only, and also give you the organization of the tableau, because then you can get all the information that you need from the tableau. Yeah, and yes, but before that, so as I said that we need the quantities Cj minus Zj also. So, to compute Cj minus Zj's for all j, we again use a iterative scheme. Okay. So, the idea is that, yeah. So, the same iterative scheme I will try to use, except in an extended way. Okay. So, consider add the objective function rho as the 0th row, and where 0th row where. So, essentially I am saying that is consider the extended basis matrix 1 CB 0 B. So, I have added the objective function also as a part of the constraints, right. In other words, what we are saying is that I will write down, since you have minimization of z equal to summation Cj xj, j varying from 1 to n, what I am suggesting is that we write this as, we just consider this as an equation. So, it will be minus z plus summation Cj xj, j varying from 1 to n as 0. So, to the already given constraints A x equal to b, I am going to add this as also a equation, right. And therefore, my basis matrix will then become m plus 1 by m plus 1. Okay. So, this is now m plus 1 by m plus 1, and if you look at the inverse of this, now this you can sit down and verify for yourself, would be actually 1 minus Cb b inverse 0 b inverse. Remember, I have added one more variable, and that is why this column, because this is minus z. So, here the corresponding column z does not appear in any of the equations. So, therefore, the corresponding column is minus 1. I have to I mean corresponding column is 1 0 0, because I need to have a m plus 1 by m plus 1 matrix. This is the whole idea. So, this inverse will be this, right. Now, if you multiply 1 minus Cb b inverse 0 b inverse with Cj and Aj. So, you pre-multiply. Remember, this is what we are doing, because we need the quantities Yj's. So, that I will get from here b inverse Aj, but now I will get something more. When you multiply this with this, that means the first row here with the corresponding column, and you have, remember, added the first row. So, this will become Cj minus Zj, because Cb b inverse Aj, and this will be your Yj. So, this is really good, because I need these quantities also. And remember, before I proceed from proceed with the simplex algorithm, that means from one basis to another, I need to know whether my optimality criteria is being satisfied or not. So, if I have all these Cj minus Zj's for the non-basic variables at hand, then I can first scan these numbers, and if there is any negative number, then I will proceed with the simplex algorithm. And of course, as you have seen that even if this held and then you discover this condition, then of course you will stop. So, I definitely need to have the quantities Cj minus Zj's with me, right. Okay. So, therefore, the idea is that you maintain this as an equation, and you consider the expanded basis, and then you keep computing the inverse. And since these elementary row operations, the pre-multiplication, executing the elementary row operations is equivalent to pre-multiplying by the basis inverse, and in this case it will be the extended basis inverse. So, we can keep updating these numbers. Yes, maybe there has been a little hasty here, but we can keep going back to the calculations, and so there should be no problem, in the sense that this is Cj minus Zj by Yj, and you see that the Cj minus Zj for a basic variable, for a basic variable xbi, the Cj minus Zj will be Cvi minus Cb b inverse bi, right, because the Zbi would be Cb b inverse bi, but b inverse bi is, what is b inverse bi? B inverse bi is Ei. So, this will reduce to Cbi minus Cbi, which is 0. So, for the basic variables, the corresponding relative cost, which is always 0, right. And so, when I want to update, so in other words, when I want to update this column, I am going to pivot on Yrj, then I also make this number as 0, because Aj is now going to enter the basis. So, it has become a basic column, and the corresponding variable is basic variable. So, the new relative price for xj should be 0. So, therefore, in my pivoting, since I am making this column as ER, I make a 0 here, and then I would have updated the whole tableau. So, let us hope that if I have missed out on something or the order has been a little different, then when we do the computations, try to make it more streamlined. Okay. So, let us now take up this example. I will introduce an objective function for you and go on explaining the computations. So, you can so you can take, suppose I am saying that you minimize z equal to x1 plus 2x2 plus 3x3 plus x4 plus x5. Okay. So, this is your new problem, a simplex linear programming problem. Let me write down the tableau for you. Yeah. So, when you begin the tableau, this is x1, x2, x3, x4, x5, right. And remember, we said that we will write the objective function as the first row. I am not writing, you can maybe, if you like, you can say minus z here, then but this column we will not carry, because this will always remain as part of the basis. So, I will not write anything here. Then this would be your 1, 2, 3, 1, 1, and remember, right now this value is 0, right. Then you have your, so let us just to separate it from the equality constraints, we now do this 1 minus 2 and 5, 2, 1 and 3, and this is okay, x3, x4, x5 are all units. So, this is 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. Then you have here 6, 4, and this is 16. Okay, 6, 4 and 16. So, this is your, yeah. Now, another point which some of you may have, I mean, you may have thought of this question is that see, what I am starting with this system of equations and I am doing elementary row operations. So, I hope you all are aware of the fact that elementary row operations do not change a system of equations. So, that means, when I do elementary row operations, the new system will have the same set of solutions as the original one, and therefore, I can very freely go on doing these elementary row operations, and we try to reduce the system of equations to get a basic feasible solution, then go on to another basic feasible solution, and so on, right. So, this is the thing, and now you see that these numbers are all non-negative. So, I have a ready-made starting solution. I can choose my B to be A3, A4, A5. There is a simplification, and of course, we will also have occasion to sometimes choose a basic feasible solution which is not as easily available. In this case, it just happens that I have a matrix, identity matrix. Therefore, my basic feasible solution is simply, because otherwise your basic feasible solution is given by B inverse B, but B inverse is identity. So, in this case, it is simply B, and since B is all non-negative, so I can say that I have a starting feasible solution, basic feasible solution, right. Okay. Now, this simplifies lot of things, because in this case, what is your yeah. So, now you need to compute your CB B inverse, right, because since B inverse is identity, what about your Yj's? Yj is B inverse Aj, which is also Aj, because B inverse, B is I, so B inverse is I, right, fine. So, now the only thing is that I want these quantities, the top row, to read Cj minus Zj, and for that the condition is that these numbers should be zeros, right. So, if I do that, then I would have a extended basis inverse. So, now what happens is, here you see that in order to make a 0 here, I simply multiply this by 3 and subtract, right. So, 3 times if you subtract here, what will you get here? 3, so this will be minus 2, 3, 2, minus 6, minus 4, this is 0, this won't change, and 3 times this is minus 18. So remember, the value is right now what? The objective function value, this is minus z. So minus z is minus 18. Okay. Then to make a 0 here, I simply, in fact you see that this is 1 1, so I add the last 2 rows and subtract. So add the last 2 rows, this gives me 3 and subtract. So minus 3 minus 5. Then 4 and minus 4, this becomes minus 8, and this is 0 and this is 0, adding 20, subtracting minus 38. Minus 38. So this tableau now gives you the Cj minus Zj's at the top, because you see this thing is 1 0 0. So what is your basis? Your basis consists of this column and these 3 columns, and this is an identity matrix of type 4 by 4. Okay. And so I have, that means, multiplied the whole tableau by the extended basis inverse, and therefore, and these quantities therefore give me the Yj's, and these give me the Cj minus Zj. And you can verify that since your solution here is basic feasible, x3 is 6, x4 is 4, x5 is 16, you can actually verify the value of the objective function. 3x3 is 18 plus 4 plus 16, which is 38. Right. So remember always that this value here reads the minus of the objective function, because I have minus z plus this equal to 0, right. And I made the objective function, I wrote this as, actually this equation I converted as minus z plus this equal to 0. So when you do operations, you get a number here, your minus z is equal to that number. So z will be equal to the minus of this number. So this gives you this, right. And you see that here the optimality criteria. So therefore, in the simplex algorithm, you have this tableau representation of the whole problem. This gives you the information that what is your current basic feasible solution, what are the relative prices corresponding to the given basis, and then since the optimality criteria is not satisfied, I can, okay, just to follow Danzig's rule, I will enter, I will say that this is a candidate for coming into the basis, because Cj minus Zj is negative, right. So then this is minus 8, and now I want to decide what will be the pivot element. Okay. So then remember, we take the positive entries, all the entries are positive here. So the ratio, corresponding ratio will be 6 by 2, which is 3. The ratio here would be 4 by 1, which is 4, and the ratio here is 16 by 3, which is 5, 1 by 3. So obviously this corresponds to the minimum ratio, and therefore my pivot element is this. Okay. So therefore I have to now make convert this column into 0 1 0 0. So yeah, so we will quickly do this, and that is the idea here. So if I, that means I divide this by 2, so this makes it this, this is this, and you see that this becomes 3. Yeah, okay. And now you have to make a 0 here, a 0 here, and a 0 here. So when you do it 8 times, you add 8 times, you add here. So yeah, if there are any mistakes, you can correct them, because this is 4, so this becomes 1, this becomes 0, this is 4, and 8 3s are 24. 24 you add here, that becomes what? 14, I think. Okay. Just check the calculations. Okay, minus 14. So you see that from 38, the value has now come down to 14 of the objective functions. It's reducing, right? And therefore this happens, right? Now I just subtract this here. So let's quickly do this. 0 minus 5 by 2 minus half this will be 1. See, that's all why I want to ensure that your new basic feasible solution, that the new solution that you obtain will be basic feasible. Then 3 times you subtract from here quickly. So 5 minus 3 by 2 will be how much? 10. This will be, or you're multiplying it by 3. So 5 minus 3 by 2, 10, 7 by 2, I think. Okay, 0 minus 3 by 2 and 9. So this will be 7. Okay. So now this is your new basic feasible solution. See the Tableau, again you get this identity matrix of 4 by 4 size. The solution is feasible here, the value has improved here, and your optimality correct. So now the top row gives you the new Cj minus Zj's. You scan them, you find out that there is still some negative entry here. That means this will be the next candidate to become a basic variable, and the corresponding column will come into the basis, and then we can proceed with the simplex algorithm. So I will do some more pathological cases and try to show you unboundedness case. I will try to take up an example to show you how you encounter unboundedness.